Okay, so hello everyone. We're going to keep talking about randomized linear algebra sketching algorithms. Last time we started with approximate matrix multiplication, where you measure error in the Frobenius norm. And we said there is a sampling-based approach where if you're trying to multiply A transpose B, what you do is you you repeatedly, let's say m times, sample a row, right? So we said before A transpose B is equal to the sum of AI BI transpose, right? Where I goes from 1 to n. So you can express that product as a sum of n outer products. So if you sample one at random and appropriately scale, that'll be an unbiased estimator. And the question was, how many do you need to sample? And also, what's the best distribution to sample from? And it turns out that the right distribution is not the uniform one, but rather to sample I with probability proportional to the product of the norms of AI and BI. I apologize, the video for last lecture got up a little late. It is up on the website now, and the notes will be there soon. I did not do the analysis of the variance in class. That's going to be in the notes, but I did do the show you that it was at least an unbiased estimator. So that was the original approach. The DKM approach is Drenaeus, Kanan, and Mahoney for approximate matrix multiplication. That was via sampling. Well, the one downside of that is, it is dependent on the actual matrices A and B, because you need to know what the row number of A and B are. So if you're in a setting where, for example, A and B are being updated in some, say, streaming fashion, well, how can you choose the sampling probabilities at the beginning? You don't know them because you don't know A and B. So another thing you can do, which gives you similar results we're going to see now, is to use a JL kind of approach, where you approximate A by pi A. Think of pi as a kind of JL matrix. You approximate B by pi B, and then you approximate A transpose B by pi A transpose pi B. Okay. And you can show that as long as your JL distribution is good and you have enough rows, your Frobenius norm of the difference will be small with high probability. I'm going to show you that now. And I should mention, by the way, that even the sampling approach is also approximating A transpose B by pi A transpose pi B. It's just that pi is not a JL matrix, it's a sampling matrix, right? Where, what does a sampling matrix mean? It means that each row of pi has a 1 in a random location corresponding to the I that you sampled, and zeros everywhere else. Normalized by square root of pi, like we did last time. But again, that pi is going to be drawn from a distribution that depends on A and B, because the sampling probabilities depend on A and B. Okay, so good. Now let's try to understand, why should the JL kind of approach work for approximate matrix multiplication? And I hinted at it last time, right? So the point is, what is A? A is this matrix, A1 transpose all the way down to AN transpose. And then B is this matrix, B1 transpose, BN transpose. And pi A transpose, actually, I guess I should. So now I think what I want to do is actually change rows and columns. So pi A transpose pi B. So what is that? If you look at the ijth entry of that, it's saying, so look at the ith column of pi A and the ith column of pi B and take their dot product. So actually I got a little slightly dyslexic here. For the purposes of this, I think what I want to do is I want to actually write it the other way around. So let's say this is A1, this is B1. So, right, so if you apply pi, that means you're applying pi to the matrix column by column. So pi A looks like, the first column here would be pi A1, the next column would be pi A2, etc. So you're taking the dot product of the ith column of pi A with the jth column of pi B. So this is just pi AI data with pi bj. And I apologize again. I guess I turned subscripts into superscripts into subscripts, so let's just be consistent. So, and then if you take minus a transpose b, that's going to be minus ai dot bj, right? So if you look at, this implies that if you look at the Frobenius norm squared, pi a transpose pi b minus a transpose b, Frobenius norm squared, this is just the sum over all ij of pi ai dot pi bj minus ai dot bj squared. So already you can imagine doing a kind of union bound argument. And in fact, if you look at, the JL approach I mentioned was first introduced by Charlotte in 06 for approximate matrix multiplication. And if you look at his paper, I mean, this is basically what he did. He said, look, if I preserve distances, I preserve dot products. So all these dot products are close to what they should be. If I union bound over all ij, then I can say that all these dot products are close for all ij simultaneously, and then therefore the sum will be close to what I want. So that was his original argument. You do lose something though, because you have to union bound over all I and j, which means that with JL your failure your dependence on the failure probability is log 1 over delta. So if you're union bounding over all these things, you need to set delta to be polynomially small to union bound, which means you're going to pick up an extra log factor in your bound from that, right? Log dimension factor. I'm going to show you an argument now that I think it's worth internalizing what's really happening in this argument, because it's the useful, I think, way of thinking in general for other kinds of probabilistic analyses. It turns out that union bound is 100% wasteful, and you can get a bound as if you're only trying to preserve a single vector. Even though you're preserving the sum, you don't have to union bound on each summand individually. Okay, so how do you do that? So definition, a distribution D satisfies the, let's call it the epsilon delta p JL moment property. Okay, if for all z of unit norm, we have that the expectation over pi of, let's look at, I guess, pi z L2 norm squared minus 1 to the pth power is at most epsilon times delta to the 1 over p. Okay. And here I'm assuming here that, let's say, p is something that's at least 1. Okay. So what is this good for? I mean, why am I introducing this? The utility of this is, right, like if you're trying to prove that, let's say, a probability over pi coming from this distribution, and by the way, this pi is also coming from this distribution. If you want this to be true, that you have the JL moment, that you have distributional JL. Distributional JL says that this thing is small, pi z L2 norm squared minus 1. The probability that this is bigger than epsilon is small, right? That's what DJL says. But if you do, if you raise both sides to the pth power and do Markov's inequality, you know that this is always true. This is at most the expectation over pi coming from D of pi z L2 norm squared minus 1 to the pth power. Oh, and I guess I should have said, well, this should be epsilon to the p times delta. That is what I should have said. Over epsilon to the p, right? So if your distribution D satisfies the JL moment property, it means that the numerator is at most epsilon to the p times delta, which means that this thing is less than delta, less equal to delta, if D satisfies the epsilon delta p JL moment property. Okay, so I mean, satisfying the JL moment property is, it's just a fancy way of saying that the distribution gives you DJL via Markov's inequality on a high enough moment. Okay, that's all it's really saying. And it turns out that kind of all the distributions that we've been talking about so far that give you JL, do have the moment property for some choice of epsilon, delta, and p. So for example, take the count sketch matrix where pi looks like this. Each column has exactly one non-zero, which is a plus minus one, and the rest of the column is zero. And let's say this is m is the number of rows, right? This has the epsilon delta pjl moment property, where basically, so count sketch, where m is at least some constant times 1 over epsilon squared delta, and p is 2. In other words, if you look at the variance of pi zl2 norm squared, now, if you bound the second moment, then you can basically prove that the probability of deviation is at most epsilon, with probability at least 1 minus delta, as long as m is at least 1 over epsilon squared delta. Right? That's just via the variance bound. Okay. So essentially, you prove that the variance is roughly 1 over m, or O of 1 over m. Okay. So we did this before when we were talking about kind of speeding up the AMS sketch via a sparser matrix. Of course, 1 over delta is not great. We usually like m to be log 1 over delta. So you can get like, let's say IID plus minus 1 entries. How do we analyze that? We analyzed it using the Hansen-Wright inequality, right? Which really is a bound on all the moments. And if you unwind that proof, inspect it, look at what moment did we use exactly, to get the delta failure probability. We use the log 1 over delta moment. So here you can set m to be something like log 1 over delta over epsilon squared, and p to be something like some constant times log 1 over delta. Sparse JL is another one. Basically similar thing, with S being log 1 over delta over epsilon. You can also even do it with fast JL. If you do it with fast JL, I think you're going to end up needing P to be a little bit bigger if you unwind kind of what moment do I really need to make the whole thing work. I think you end up getting away with something like P is like roughly log of 1 over epsilon delta, and M is something more, that's a little different. So M is going to be something like something maybe like log 1 over epsilon delta, log 1 over delta over epsilon squared. Maybe a little bit better than that. I'll put the precise thing in the notes. But the point is, yeah.
Where do the values of P come from? Like, are they related to M?
Yeah, I mean, so the point is, I guess, right? If you look at, let's say, I don't know, analyzing the second one here, IED plus minus 1 entries. We used Hansen-Wright, right? So if you remember, let's say this one right here, right? We used Hansen-Wright. Let's call this this is the error random variable. Let me call it something. Let me call it Z. Right? It's a quadratic form, right? It looks Z transpose. So remember now, we had this thing before we said like Z transpose pi Z, right? Can be expressed. It's just the same thing as sigma transpose A sigma, right? Where A was this block diagonal matrix. So if you look back in the notes, you can see this all over again, but A looks something like ZZ transpose, ZZ transpose, ZZ transpose. And there's a 1 over M here, right? And Hansen-Wright said that if you look at this error random variable and look at its P norm, it's at most, up to a constant root P times the Frobenius norm plus P times the operator norm, right? And then, the way you might, the other way we've been talking about Hansen-Wright is like for all lambda greater than 0, the probability that Z is bigger than lambda is at most up to a constant like e to the minus C lambda squared over Frobenius squared plus e to the minus C lambda over operator norm. But these two things right here are equivalent to each other. Right? So to say that for all P bigger than or equal to 1, you have norm bounds, moment bounds, and to say that you have tail bounds for all lambda bigger than 0. Like those two are equivalent to each other, and that's, if you want to see again a proof of that, that's in the notes in the probability review section. But the point is, we've been analyzing multiple of these, like sparse JL and the middle one, plus minus one entries. We analyzed both of them using Hansen-Wright. Hansen-Wright is equivalent to bounds on the moments. So if you just inspect the proof and look at like which moment did we use, which P did we use to get the results, it turns out that we used P to being something like log 1 over delta. And we set M to be log 1 over delta over epsilon squared. So you can go back and look at the proofs and realize that this is what we were doing, but indeed it's what we were doing. So all these things we've been analyzing so far have been all based on moments. Even Kramer-Ward, right? Kramer-Ward ultimately was also using Hansen-Wright. Hansen-Wright, again, is just based on moments. So yeah, so all these things that we've been talking about do have the epsilon delta P GL moment property for some P. Okay. Any other questions? Okay. So now that we've introduced this concept, first let me talk about how to use it for kind of dot products. So suppose D has the epsilon delta P JL moment property. Then for all xy of unit norm, if you look at the dot product, so here, let's look at this, pi x dotted with pi y minus x dotted with y. Look at the p norm of that. That's going to be at most epsilon times delta to the 1 over p. Remember, the p norm is the pth moment raised to the 1 over pth power. So if you just raise both sides to the pth power, what I'm saying is that the pth moment of this difference in dot products is also bounded by epsilon to the p times delta. So the definition of JL moment property just says that you preserve norms, right? Your moment bounds on the difference of the norms is small. And just having that alone implies the same bound on dot products. Okay. And why is that true? So proof of this, it's something similar to something you've already seen, which is just the observation that, look, x plus y L2 norm squared is equal to x squared plus y squared plus twice the dot product. And also x minus y squared is equal to x squared plus y squared minus twice the dot product. Okay. Which implies if you just move things around, you'll get that x dotted y is equal to 1/4 x plus y squared minus x minus y squared. Okay, this follows just by rearranging, nothing fancy. Okay, so now let's do this both to x dot y and pi x dot pi y. This implies that pi x dot pi y minus x dot y p norm is equal to, let's rewrite x dot y and rewrite pi x dot pi y, equal to 1/4 times, basically what I want to say is pi x plus pi y L2 norm squared minus x plus y L2 norm squared minus pi x minus pi y L2 norm squared minus x minus y L2 norm squared p norm. Okay, so I just rewrote x dot y using the identity above, and I rewrote pi x dot pi y using the identity above, and did a little bit of rearranging. And then now I can do triangle inequality. This is at most 1/4 times pi x plus y L2 norm squared minus x plus y L2 norm squared p norm plus pi x minus y L2 norm squared minus x minus y L2 norm squared p norm. And then I can multiply by, multiply and divide by the same thing. So basically multiply by 1. What I mean by that is, let's just divide by x, oops. Let's just divide by the norm of x minus y here. And let's divide by the norm of x minus y. And that's okay as long as we multiply it back on the outside. So let's multiply it back. We're going to multiply it back by x minus y squared because there's a squared here, right? So if we divide by it, we have to multiply by the square. And let's do the same thing here. Divide by x plus y norm, divide by x plus y norm. And then here, on the outside, multiply by the square. Okay, does that make sense? Okay, good. And then now, what do I know? This is pi times z L2 norm squared minus z L2 norm squared, where z is, for example, x plus y over the norm of x plus y. So z is a unit norm vector, right? This is what I'm calling z. Like this vector, let's say I call it z. It's a unit norm vector, right? So I can apply the fact now that D has the epsilon delta p JL moment property. And I can say, therefore, this moment is bounded. So this is at most 1/4 times. Here I get, I'll pull it out to the outside. Epsilon times delta to the 1 over p. And then I have that 1/4. And then here I have x plus y squared, because I have this part. So I have to keep that, x plus y squared. Okay. And similarly, I have the same thing over here, but I have plus x minus y squared. Okay. And then again, so now there are no more p norms, right? I already applied my p norm. And then now I can again use the parallelogram rule. This is the same thing as, this should be a, this is a plus. So this should be x squared plus y squared plus twice the dot product. This is x squared plus y squared minus twice the dot product. So these dot product thingies cancel. What's the norm of x squared? Right. X has norm 1, y has norm 1. So this is also known as 4, right? 1 plus 1 plus 1 plus 1 is 4. So this is equal to, and the 4's cancel, epsilon times delta to the 1 over p. Okay. So just knowing that I have a certain kind of moment bound on like preserving distances or preserving norms of vectors automatically implies that I have the same quality of moment bound. I don't even lose a constant factor. I have the same quality of moment bound when I'm trying to preserve dot products. Okay. So now let's go back to understanding approximate matrix multiplication using JL. Okay. So back to approximate matrix multiplication with JL. The claim is if the distribution D satisfies the, let's say, epsilon delta P JL moment property for some P which is at least 2, then the probability that I deviate in Frobenius norm from the true matrix product by more than epsilon times the Frobenius norm of A times the Frobenius norm of B is at most delta. Okay. So all these things that we showed satisfy JL in the past, like the count sketch matrix, for P equals 2 with a bad M, or sparse JL or fast JL or whatever, since they all satisfy JL and P, for some P, I basically automatically get that they give you approximate matrix multiplication as well, without having to set delta to be smaller. You don't have to set delta to be smaller to union bound or anything like that. It just automatically works. Okay. So good. So let's try to understand this. So let's define M to be pi A transpose pi B minus A transpose B. And we already said that then you have something like Mij is equal to pi AI dotted with pi Bj, where AI is the ith column of A, Bj is the jth column of B, minus A transpose AI dot Bj, sorry. So that implies that M Frobenius norm squared is equal to the sum over all ij of this thing squared. And again, what I'm going to do is I'm going to write this. Let me define now AI tilde, just define it to be AI divided by its norm. Okay. So I can write that this is the same thing as pi A tilde dot pi bj minus AI tilde dot bj tilde. And then let me multiply it by the norm of, multiply back by what I divided by. So multiply back by the norm of AI times the norm of bj. So the Frobenius norm squared then is the sum over all ij of this thing squared, pi ai tilde, pi bj tilde, minus ai tilde, bj tilde, squared times ai L2 norm squared times bj L2 norm squared. And kind of, why am I doing all of this? Like, why? So, right, the point is, where am I going? Where I'm going is the second moment method, right? Where I'm going is, look, I'm trying to bound the probability that the Frobenius norm is large. I say, look, the probability that the probability the Frobenius norm is large is the same if I square both sides. So it's the same as if I square both sides. And then I can apply Markov. That's less than the expectation. Actually, let me raise both sides, in fact, to the pth power, I should say. That's less than the expectation of m Frobenius norm to the p divided by lambda to the p. So the name of the game right now is try to get a bound on this thing using the JL moment property. And if I can do that, then I'm golden, right? Then I can just plug it into this Markov and I'm done. Okay. So now we understand at least what the Frobenius norm squared looks like. Okay. So now I'm trying to understand now the p norm, right? Because this is the p norm raised to the p. The pth moment is the p norm raised to the p. So I want to understand the p norm. So let's look at the Frobenius norm of m, p norm. That's the same thing as the expectation of the Frobenius norm raised to the p to the 1 over p. But Frobenius norm has a square root in it, and that makes things more complicated for me. I prefer dealing with the square of the Frobenius norm because then there's a summation there and it's more linear. So what I'm going to do is I'm just going to square this and then raise to the p over 2th power. I haven't changed anything, right? That's still the Frobenius norm to the p. It's just that I just wrote it in a different way. And I'm going to use the fact that, you'll see soon, I'm going to use the fact that the p over 2 norm is still a norm. And that's why I required actually that p is at least 2. That way p over 2 is at least 1, so I have a norm. And then this 1 over p on the outside is the same thing as like 2 over p. And then if I take the square root of the whole thing. So this is also known as mf squared p over 2 norm all raised to the 1/2. Okay, does that make sense? Okay, so now good. Let's try and now understand this. Let's try and bound the p over 2 norm of mf squared. Okay. So now we're just going to write out what mf squared is. That's what we wrote above. So this is equal to, and also just to make things like not have to, not be bogged down with too much notation, let me just call this random variable, like this is a random variable because it depends on pi, this one right here. Let me just call this like xij. Okay, so that's a random variable. It's defined without the square. Okay, so now I know that the Frobenius norm squared, I can write that thing as the sum over all ij of ai L2 norm squared, bj L2 norm squared, xij squared, p over 2 to the 1/2. Okay. And now I can do triangle inequality. Okay. And then this is, at most now, the sum over all ij of, well, remember there's a square root up above. So when I pull out a constant factor on the inside, I have to make sure to take the square root. So I'll pull out ai L2 norm squared, but I have to square root it. So I don't have the square root anymore. So I have the norm of ai times the norm of bj times xij squared p over 2 to the 1/2. Okay. But again, now I can just, what is the definition of, what does this mean? This means, this thing here means expectation of xij to the p. No, it's actually absolute value to the p. To the 2 over p to the 1/2. So to the 1 over p. Right. So this xij squared p over 2 norm all raised to the 1/2 is again a really fancy way of saying the p norm. So this is just equal to the sum over all ij of ai bj times the p norm of xij. Again, what is xij? It's this difference of these two dot products, right? Where ai tilde is a unit norm vector, bj tilde is a unit norm vector. So we can apply the lemma on the previous whiteboard to say that by the JL moment property, this thing here is at most epsilon times delta to the 1 over p. So overall, this whole thing is at most epsilon delta to the 1 over p times the sum over all ij of ai times bj. And then now I just finish it with Cauchy-Schwarz, right? Cauchy-Schwarz says, right, x dot y is at most the norm of x times the norm of y. So this is at most epsilon delta to the 1 over p times the sum of ai squared square root times the sum of bj squared square root. What's another name for this? Like, what is this? Make sure we're on the same page here.
The Frobenius norm of B.
Yeah, exactly. It's the Frobenius norm of B. I'm just summing up the entries like squared column by column, basically, right? And similarly, this is the Frobenius norm of A. Okay. So then now you plug that all in here, right here. Just set lambda to be exactly this. Lambda is epsilon times the Frobenius norm of A times the Frobenius norm of P. So you raise it to the Pth power, you get epsilon to the P, AF to the P, BF to the P in the denominator. And then the numerator is exactly all of this raised to the P. Right? You take that thing and you raise it to the P. That's what goes in the numerator. Frobenius norm to the P cancels, BF to the P cancels, epsilon to the P cancels, and the only thing you're left with is delta to the 1 over P raised to the P, which is delta. Right? So your failure probability is at most delta, which is exactly what you wanted to show. Okay. So good. So that's all I want to say about that, is that you get, having this gel moment property gives you AMM with respect to the Frobenius norm for free. Questions about that?
So when you said that like norm P of xij is less than or equal to epsilon delta to the 1 over P, that was using the like the JL.
You're saying the last inequality down there? I was, the one right before Cauchy-Schwarz?
Yeah.
I was using this, right? I was using this
plane. Right, yeah.
Right, because xij is exactly of this form. Xij is some difference of dot products with unit norm vectors.
Yeah.
Right.
And before that, when you like split up the norm using triangle inequality, we also like relying on the square root satisfying the triangle inequality. Like I guess that's true. I just hadn't thought about it before.
Yeah, so if you don't want to think about it, yeah, so we are using the fact, you're right, that like the square root of a plus b is at most the square root of a plus the square root of b. Right? If you just square both sides. The left-hand side is a plus b. The right-hand side is a plus b plus more. So, yes, I was using this fact. Good observation. Any other questions? Okay. So good. So that's Frobenius norm approximate matrix multiplication. Let's now try to move to another norm. What about approximate matrix multiplication with the operator norm? So what I want is that, ideally I want A transpose B minus, say, some pi A transpose pi B operator norm to be less than, say, something similar, A epsilon times operator norm A times operator norm B. So it's going to seg into, I guess, something that's more interesting, which is if I do this, we're going to focus on, like B equals A. Okay. For the rest of the lecture. I mean, you can do stuff for B not equal to A, but in the applications that we're going to see of this, it's most interesting when B is A. So I'm going to focus on that. So what does this mean? This means that A transpose A minus pi A transpose pi A operator norm is at most epsilon times A squared. Like, what is the operator norm? The operator norm is, these are both symmetric matrices, right? Like, the left-hand side, the left-hand side of this is a symmetric matrix. This thing is kind of the soup over all Z of unit norm of Z transpose times that matrix Z, right? Which is the same thing as like the soup over all Z of unit norm of pi AZ L2 norm squared minus Z L2 norm squared. And then the right-hand side, this thing is also the same thing as the operator norm of A transpose A. So the right-hand side is like, so this is saying this is at most like the soup over all W of a W L2 norm squared, right? So to say that pi is letting you do AMM with respect to operator norm is basically the same thing as saying that this is true. It's the same thing as saying that this inequality is true. But we're going to get something that's even stronger in today's lecture, which is the notion of what's called the subspace embedding. We will study pi such that for all Z of unit norm, we have that pi A Oh, there's an epsilon here, right? There's an epsilon. Pi AZ L2 norm squared minus Z L2 norm squared, which is just 1, right? I mean, this is also just 1. Minus 1 is less than or equal to epsilon times the same Z. So instead of the super over W, it's the same Z. So that's AZ L2 norm squared. Oh, sorry. I just realized
Should it be
this should have been
the
AZ.
norm of AZ?
This should have been AZ. Yeah. So forget that. It's not 1. AZ L2 norm squared. And then similarly, this should be AZ. Okay. So what this is saying is, for any vector Z, pi AZ has roughly the same norm as Z. Okay. And this, by the way, is called, this concept is called like an epsilon. If this is true, we'll say that pi is an epsilon subspace embedding for the column space of A. Okay, so what's the definition? Let me give you the definition of a subspace embedding. Right. So definition, pi is an epsilon oops, why is my pen weird? Pi is an epsilon subspace embedding for, let's say, some linear subspace E, which is, say, is a subset of RD, if for all Z and E, let's say for all X and E, it doesn't matter. If you look at pi Z L2 norms, let me call it X actually. Pi X L2 norm squared has roughly the same norm as like 1 plus epsilon. Pi X L2 norm squared has roughly the same norm as X L2 norm squared. Right. If pi satisfies this, I will call pi an epsilon subspace embedding for E. Okay. And now notice that I want to write an equivalent way, equivalent way of saying this. So what is a subspace? Well, any subspace has an orthonormal basis. So like equivalently, let U, which is, let's say, it's a D by K, it's a D by dim E matrix, have orthonormal columns forming a basis for E. Then, first of all, without even the orthonormal, just the fact that it's a basis, that means that E can be written as the set of all vectors Z or X such that there exists a Z, where X is equal to UZ. In other words, this is the same as the set of all vectors UZ where Z is an RK. And actually, let me make, I'm just going to change notation on you a little bit. Sorry for this. It's going to make things simpler later. I'm just going to say that D is the dimension of E, and E lives in in Rn. So E is a D-dimensional subspace of Rn. So that means U is an n by D matrix. So E is just the set of all vectors of the form U times Z. Okay, so now what does it mean to be a subspace embedding? An epsilon subspace embedding. What does it mean? It means that for all Z and RD, pi UZ L2 norm squared is less than or equal to 1 plus epsilon times the norm of UZ L2 norm squared is at least 1 minus epsilon times the norm of UZ squared. What is UZ L2 norm squared? That's the same thing as Z transpose U transpose UZ, right? This is the norm of UZ L2 norm squared. But U has orthonormal columns, which is the same thing as saying U transpose U is the identity matrix, right? What's the ijth entry of U transpose U? It's the ith column of U dotted with the jth column of U. So if I equals J, it's 1. If I is not equal to J, it's 0 because the columns are orthonormal. So this is the same thing as Z transpose Z because U transpose U is identity, which is the same thing as Z L2 norm squared. So this is the same thing as saying that 1 minus epsilon Z L2 norm squared is less than or equal to pi U Z L2 norm squared is less than or equal to 1 plus epsilon Z L2 norm squared. Or if I subtract Z L2 norm squared from both sides, this is saying that pi U Z L2 norm squared minus Z L2 norm squared is at most epsilon times Z L2 norm squared. This is like for all Z. And this is the same thing as saying that the operator norm of pi U transpose pi U minus the identity matrix is at most epsilon. Okay. So that's what I want to emphasize, namely this definition of what it means to be a subspace embedding is equivalent to this other notion. If I had defined subspace embedding by the bottom box, it would have been equivalent to the top box. Okay, which by the way, looks a lot like, it looks a lot like JL. Like think of DJL. What does DJL say? DJL says that for all unit vectors, let me just write this down and you can see the similarity. Say DJL says that kind of for all unit vectors U, what does it mean to be a unit vector? So for all U in RD, such that U transpose U is 1, meaning it has unit norm, the probability over pi that pi U L2 norm squared, which is the same thing as pi U transpose pi U, minus 1. 1 is, of course, just the 1-by-1 identity matrix. The probability this is bigger than epsilon is at most delta, right? That's what it means that the distribution D here gives you distributional JL. And you can imagine then defining something similar for subspace embeddings, where you say for all. Oh, and actually, maybe I should have. Let me call this N. So I can define something similar where I say, look, U is not a vector anymore. U is a matrix. So a vector is just an n-by-1 matrix. Let's make it an n-by-d matrix. And instead of U transpose U equals 1, I'll say U transpose U equals the identity, the d by d identity. And let me here also put d by d identity, and let me put operator norm. So kind of syntactically, this looks just like a natural generalization of distributional JL. And this is what I'll call an oblivious subspace embedding. So a distribution D over pi satisfying the above is called, and let's say epsilon D oblivious subspace embedding. Right, what it means is kind of for all linear subspaces E of dimension D, with good probability, a random matrix drawn from this distribution will be a subspace embedding for that subspace for E. Okay. Right, and it's a natural, if you write it this way, it's a natural generalization of distributional JL. Okay. Now, just recall The definition of subspace embedding for a particular subspace, there's no randomness in the definition. Like I am allowed to pick, a deterministic matrix that is a subspace embedding, right? Or I can do something that's kind of oblivious like this, where I'm picking a random matrix that doesn't even look at the subspace. We'll see different ways of constructing subspace embeddings now. Some oblivious, some not even random. So before I talk about how to get subspace embeddings and what they're good for, are there any questions about what the definition of a subspace embedding or the definition of an oblivious subspace embedding? Or is that all clear?
So these D's you added on like a modification.
Well, D, yeah. So D is so you can think again here when I've modified it with the red ink, U is now a matrix, an n by D matrix with orthonormal columns. So you can view the columns as the basis, an orthonormal basis for some subspace, namely for the column space of U. Okay. So this is just saying that with high probability, a random pi, for any fixed subspace of dimension D, a random pi will preserve it with high probability. It'll preserve all vectors in that subspace with high probability.
And it's oblivious because it works for any subspace.
It's oblivious because you pick pi without even knowing what the subspace is. Sort of like JL. You pick your JL embedding without even knowing what the vectors are that you're trying to preserve. Okay. So good. So, so first let me talk about like how do you get subspace embeddings? Okay. So one is, so usually for us, the subspace is given as, not that it matters, but usually for us, we're going to see like in the applications, the subspace is often going to be, the column space of a given matrix. So I'm just going to give you a matrix A, which is some big matrix. And let's say it's a very tall, usually for us, A is going to be like this. A very tall matrix that's not too wide. So think of it as like n by D. And I'm going to want to preserve its column space. Its column space has dimension at most D because there are only D columns. Okay. So kind of the subspace is implicit in the sense that I don't actually give you as input an orthonormal basis for the subspace. Given A, you could try to compute an orthonormal basis by, for example, doing Gram-Schmidt or computing the SVD of A. That would give you an orthonormal basis. But that's expensive in terms of computation. That's an expensive operation. So let's say first of all, if you know the subspace, if you know an orthonormal basis for E, let's say that it's like a matrix U, which is an n by D matrix. U transpose U is identity. E is equal to the column space of U. So if I know such an orthonormal basis, I claim that a great thing you could do is choose pi to just simply be U transpose. Right? Why? Because if X is in E, that implies that X is equal to UZ for some Z, which implies that pi X is equal to U transpose UZ, which is just Z. And we already know that X L2 norm squared is equal to UZ L2 norm squared, which is equal to ZL2 norm squared, because U transpose U is identity, right? So this is like perfect equality. This pi does not introduce any error at all. It perfectly preserves the norm of the entire subspace. And this thing maps n dimensions down to D dimensions, right?
So Jelani, the pi is just a change of basis, right? to the basis of E, right? In that case.
Yes. Well, it's. I don't. So yeah, I guess I. Right. Yeah. So you're telling me what the coefficients are if you try and express x in the basis u, you're telling me what the coefficients are. That's going to be the entries of pi x. Is that that's what you're saying, right?
I'm saying it's the change of basis from the standard basis to the basis that it would be in for E, I think, or the other way around. One of those.
Yeah. I mean, I guess it depends on what change of basis means, because we are also changing the dimension, right? Like,
oh right. Yeah.
Originally we're in dimension n, now we're in dimension d. But you can also imagine that we complete the basis into a full n-dimensional basis, but that doesn't matter because all the other things that we complete, all the other vectors we add in, are going to be orthogonal to x anyway.
Got it.
So all those dot products are going to be 0. So yeah, that would be a change of basis in the same dimension.
Okay.
Yeah.
Sounds good. Thanks.
So this is like perfect, right? Because this gives epsilon equal to 0, which is the smallest epsilon you could want, and it gets you down to dimension d. And I claim that you can't hope to get that down to dimension less than d, just for reasons of I guess kernels, right? So if you have a d-dimensional subspace and you hit it with a matrix that has fewer than d rows, then something in that subspace is going to be in the kernel. Like some non-zero vector in the subspace is going to be in the kernel, which means you're mapping it to 0, which means you're definitely not preserving its norm, right? Its original norm, let's say, was 1. Now you're mapping it to the 0 vector. You have not preserved it. So D is like the smallest dimension you could ever hope to get, and you're getting it with absolutely no error, right? The downside of this is that you need to know an orthonormal basis for E. And again, if E is given to you as, let's say, the column space of a matrix A, and A might not have orthonormal columns, then it's expensive to extract orthonormal columns from A, right? You either have to do some Gram-Schmidt or SVD or whatever, which is going to be expensive. So computationally expensive. So anyway, this is like the holy grail, best kind of bound you could hope to get. What else can you do? You can do sampling. That's another thing you could hope to do. Again, A transpose A is equal to the sum over all I from 1 to n of AI transpose. Okay. I got now. Okay, so now here, I guess I'm going back to my old ways where the AIs are actually the rows, not the columns. Sorry about the mass confusion. So you could ask yourself, well, what if I sample and I say, look, this is roughly the same thing, hopefully, as some sampled version. So sum I goes from 1 to n of, let's call it eta I over pi AI transpose, where eta I is equal to 1 if we keep row I and 0 otherwise. And, like the probability that eta I is 1 is pi. And that's why we divide by pi, so that the expectation of this thing is correct. So that this is
Jelani, you're frozen or muted. All right.
it seems I was booted out. Can you hear me?
Yeah.
Can you say that one more time?
Yes, we can hear you.
Okay, now it seems that my audio, I don't know why this keeps happening. My audio is, yeah. Okay, say hello one more time.
Hello.
Okay, great. So now it's working. And now let me get back inside of my whiteboard. Okay, so this is where we were. Good. Okay. Right. So what I'm doing is I'm going to end up with a variable number of summands because for each row independently, I'm going to decide whether to keep the row or not keep the row. So with probability pi, I keep the ith row. With probability 1 minus pi, I ditch the ith row. Eta I is this indicator random variable that keeps track of whether or not I kept the row. I divide by pi so that this thing is an unbiased estimator of A transpose A. I want the expectation of this to still be correct, to be A transpose A. Okay, so that's one thing. And again, there's a question of now what should I set the sampling probabilities to be? With Frobenius norm, approximate matrix multiplication, we said that pi should be proportional to the norm of AI times the norm of bj, or sorry, the norm of AI times the norm of bi. Is that the right sampling probability for subspace for getting a subspace embedding? And it turns out the answer is no. It turns out that the right sampling probability is something called the leverage score. It's related to the leverage scores of A. We're going to get to that soon. And then, so all of this, by the way, I should title this is how to get subspace embeddings. Okay. So option 1, you know an orthonormal basis, then it's easy. Option 2, you sample rows of A according to some distribution that you need to figure out. Option 3 is to do an oblivious subspace embedding. Okay. And so let me say a little bit more about, so the question is like, what should the distribution be, right, for an oblivious subspace embedding? So I think the first bullet here is like set pi to be U transpose. There's not really much more I want to say about that. But I do want to say more about sampling and oblivious subspace embeddings, namely, what should the distribution D be for OSEs, and sampling, what should the probabilities be? Okay. So let's talk about them in reverse order. And I think I'll be able to say what I want to say about them, and then we can move on to more applications on Monday. Okay. But actually, even before I talk about these two, I want to say what OSEs are useful for, because I've said a whole lot about OSEs so far and subspace embeddings without telling you anything about like why you should care about them. So let me give you an example application of subspace embeddings. Okay, and this is called this kind of discussion solve paradigm due to Charloche in 2006. And the idea is take a problem like least squares regression. So beta least squares is equal to the minimizer overall beta of the norm of x beta minus y, L2 norm. Okay. So you should think of X as a big matrix and Y is also a vector, and that's the dimensions have to match up. So, whoops. Okay. So, you can do some, well, actually, I can just say it kind of intuitively. So, but you can verify it by like computing a gradient and setting it to 0. So what is the beta that's the minimizer? Okay. If you just think about it, well, for any beta, x times, what is the set of all possibilities for x times beta? Well, that's just the column space of x, right? The set of all vectors of the form x beta is the column space of x.
Wait, Jelani, are your dimensions reversed for x?
Oh, for y, you mean?
Or sorry, for y, yeah.
Yeah, that's n. That's n. Yeah, y is a vector, so it only has one. Okay. So yeah, so let's just think about it. The set of all x beta is like the column space of x. which is a linear subspace of Rn. Okay, so let's look at y. Y is a vector in Rn, and you can decompose y as like y is kind of y perp plus y parallel. Like y is the part of y that lives in the subspace, that column space of X, plus the part of y that's orthogonal to the subspace. Okay, and if you're trying to minimize this L2 norm, like the best you can do is entirely kill the part of y that lives in the subspace, and then what you're left over with is just the norm of the perpendicular part. Okay, so basically you should choose beta such that x beta, you want x beta to be the projection of y onto the column space of X. Okay. And you may have seen this in linear algebra, you may not have. This should be basically, let's call it, I don't know, the projection matrix onto the column space of X. Okay, so actually, let me not write this. This should be equal to the beta such that x beta is equal to the projection onto the column space of X of y. Right, that's what you want. And it turns out that that has a form, that has something you can write down, which is equal to X transpose X pseudo inverse XY, I think. Okay. And if you don't know what the pseudo inverse is, the pseudo inverse has a definition. So what is the pseudo inverse thing? So just some background. If you have a matrix A, it can always be written as U sigma V transpose. This is called the singular value decomposition. Where U and V each have orthonormal columns. And sigma is some square matrix where the dimensions are both equal to the rank of A. And it's a diagonal matrix that has, see these numbers on the diagonal, which are strictly positive. So sigma 1 is greater than or equal to sigma 2 is greater than or equal to dot greater than or equal to sigma r. These are called the so-called singular values. So theorem, any matrix, any real matrix A has an SVD. It can be decomposed in this way. Okay. And then the pseudo inverse is just defined to be V sigma U inverse. Okay. And the property that, sorry, not U in, sorry, that's not what I meant to say. V sigma inverse U transpose. That's the pseudo inverse. And it has the property that, if you look at A plus, A pseudo inverse, what is that equal to? That's equal to U sigma V transpose, V sigma inverse U transpose. Okay, V transpose V is the identity because V has orthonormal columns. Sigma inverse is the identity because it's the inverse. So this is just equal to U transpose, which is equal to the orthogonal projection onto the column space of A. Right? The columns of U, like if you look at the SVD, the columns of U form an orthonormal basis for the column space of A, and the columns of V form an orthonormal basis for the row space of A. So that's that's one property of the SVD. So A plus is this matrix that has the property that A plus is the projection onto the column space. A plus A would be the projection onto the row space, for example. Okay. So I mean, it had, it's called the pseudo inverse because A might not be invertible. It might not have full rank, right? Or it might even be a rectangular matrix, in which case it doesn't make sense to talk about its inverse. But this thing has some properties that are similar to the inverse, right? If you take AA inverse, you get the identity, which is the projection onto the column space or row space of A, because it's everything. But in the case that A doesn't have full rank, then A plus A and AA plus still give you that projection property. Okay. Okay, good. So, what should I say? Okay. So maybe now I'll just talk about something about runtime. Right. Okay. Maybe also I'll say something about this matrix here. So if you look at, let me also take a second to look at this. So if you look at X transpose X pseudo inverse, let's just analyze what this is. What is X transpose X? Based on the SVD, X transpose would be V sigma U transpose, right? So that'd be V sigma U transpose. That's X transpose. Times X would be U sigma V transpose. So that would be equal to V sigma squared V transpose. Then when you take the pseudo inverse, of this thing, you'll get V sigma minus 2 V transpose. And then there's an X here. So if you multiply by X times X, let's say, times X, times X, times X. X is again, I guess this should probably be X transpose. The X transpose will again be V sigma U transpose. Right? So this V transpose V is identity. This sigma cancels one of them, one of the minus 2. It makes it minus 1. And then now we want beta such that X beta is the projection of Y. So if you look at X times this, that's equal to U sigma V transpose, V sigma minus 1 U transpose. V transpose V is identity. Sigma inverse goes away. This is U transpose. Right? So that's why we're doing what we're doing. Basically, we're just using the fact that, I know this looks like a mouthful, but we're using the fact that for any matrix X, if you look at the matrix X transpose X pseudo inverse X transpose, okay, so sorry if that looks like a mouthful. This matrix is the projection onto the column space of X. That's just a general linear algebraic fact.
Didn't we just say that was just X pseudo inverse though? Like, why do we need like the extra stuff? Or you said you said AA pseudo inverse.
Yeah. So I guess the issue here is, oh, you mean like, why don't I just compute X pseudo? I mean, yes, I think I could have done the thing below as well. Like, why don't I just do, okay, sorry. So I don't like, okay, so let me back up a second. I don't want beta to be the projection of X onto Y. Right? I don't want beta to be the orthogonal projection of Y. I want X beta to be the orthogonal projection of Y.
Oh, okay.
So if I choose beta then to be this, I in fact get that. If I choose beta to be that thing, then X beta will be the projection of Y. Does that make sense?
Yeah, I think so.
Okay. So now let me say finally something about subspace embeddings. So we said that beta ls is equal to x transpose x pseudo inverse x transpose y. Now, naively with for loops, what is x transpose x? This is a d by d matrix, right? Because x is n by d, x transpose x is d by d. So it has d squared entries. And for each entry, how do you get that entry? You dot product the corresponding column of x with a corresponding column of x. So the ijth entry of this is like the ith column of x dotted with the jth column of x, which those are n-dimensional vectors. So it takes you n time. So there are d squared dot products here. Each one is going to take you n time to compute. This naively takes O of nd squared time. And that's what we're going to try to speed up using subspace embeddings. Okay. So instead, sketch and solve says, I'm going to sketch everything down to low dimension, and I'm going to solve it in the sketch dimension. So beta tilde ls, I'm just going to define as being the argmin over beta of pi x beta, minus pi y elsewhere. Okay, so it's just like what I had before, but I throw pi's into it. And for the same reasoning, this is going to be equal to pi x transpose pi x pseudo inverse pi x transpose pi y. I know that sounds like a mouthful, but that's what it is, right? Just based on the same thing we said last time. And now what's the point? Now the point is this, it's not an n by d matrix anymore. It's an m by d matrix. So this is O of md squared time plus the time to compute pi times x, right? Because we have to actually sketch it down. So we want m to be small. We're going to end up getting m to be roughly d, or some d over epsilon squared or something, but we want m to be much smaller than n. And we also want a pi which allows for fast matrix multiplication. So for example, pi is sparse, so we're going to use something like the count sketch or sparse JL. Or if pi has structure like fast JL based on the f of t, we can compute pi x quickly. Okay. So then the question is, why should beta tilde ls be any good? Right? Yes, we can compute it, but why is it good? Claim let E be equal to the span of Y as well as the columns of X. Note now the dimension of E is at most D plus 1. Then if pi is an epsilon subspace embedding for E, then if you look at the performance of beta tilde, so pretend to use beta tilde, x beta tilde ls minus y, L2 norm squared, is at most 1 plus epsilon over 1 minus epsilon times x beta ls minus y, L2 norm squared. Does that make sense? So what I claim is if you do sketch and solve, the beta that you get out is almost as good as the actual optimal beta, which is beta ls. So even though we're not solving for beta ls, we're solving for something different, it does almost as well for regression. Okay, and let's prove that. Proof. So the first thing I'll say is, if you look at pi x beta tilde ls minus pi y L2 norm squared versus pi x beta ls minus pi y L2 norm squared. So that's the difference here is one is beta tilde. Which one is less than the other? Who's smaller? Any takers?
Beta tilde is smallest because it's the argmin.
Are people still there or are you frozen? Someone type in the chat so I can make sure people are still there.
Hello.
Oh, your picture is frozen, but I can hear you.
Oh yeah, he's frozen too now.
Yeah, I can't hear you anymore now.
Okay, sorry about that. Finally, I'm back in. Can people hear me?
Yep.
Okay. So as soon as I asked the question, it seems I was booted. So let's go back.
What was the question again?
Yeah, so the question was, sorry, just give me a second. Yes. So right here, I claim that there's some inequality right here. One of them is less than the other. Who's less than who? And why?
I'm going to say beta tilde because it is defined to minimize that quantity.
Right, exactly, right? Beta tilde is the minimizer for the sketched problem. So it goes this way. And then now I can just say that this is equal to pi times something. What is that something? That something is in the subspace E, right? It's a vector which is in the column space of X minus Y. Y is also in E. So that thing is in E. So this is at least 1 minus epsilon times the norm squared of X beta LS minus Y L2 norm squared. And similarly on the right, this is at most 1 plus epsilon times X beta LS minus Y L2 norm squared. So if you just rearrange things, this implies that, you know, basically take this and compare it to this. It means that X beta tilde LS minus Y L2 norm squared is at most 1 plus epsilon over 1 minus epsilon times X beta LS. So this is like a very simple application of subspace embeddings, right? And again, if I use like an oblivious subspace embedding, then it doesn't. I should also have written, you know, there's also the time, you know, plus the time to find pi, right? But if I'm using an oblivious subspace embedding, then it doesn't take any time to find pi, or it doesn't depend on the input at all. You just choose it randomly. I want pi to be sparse or fast so that time to compute pi x is fast, and I want m to be small. Okay, so this is a very simple example. We're going to see actually there's even more efficient ways to use subspace embeddings for regression even. You don't have to rely entirely on it being a subspace embedding. That will get you m to be something like d over epsilon squared. There's a way to argue that combines subspace embeddings with AMM, approximate matrix multiplication, with respect to the Frobenius norm, that actually will allow you to get away with d over epsilon. And in fact, you can even get away with m being roughly d independent of epsilon if you use subspace embeddings in combination with something like gradient descent or iterative methods. So basically there what you do is you use pi, you use a subspace embedding to help you find what's called a good preconditioner for your input matrix. And then once you have a good preconditioner, that reduces the condition number of x so that gradient descent will converge in fewer iterations. I know what I'm saying right now might sound like nonsense because I haven't defined anything I'm talking about, but you'll see that next week when we talk more about this. Okay, so I think that's all I want to say for today. Monday, we're going to talk about how to get pi using sampling via leverage scores, as well as how to get oblivious subspace embeddings, and then we're going to see kind of more sophisticated uses of subspace embeddings for regression, for other problems as well, like low rank approximation, like clustering. Okay. So.